Hi, we are the arc valve replacement team. We were tasked with replacing the spool valve in the arc valve assembly. The arc valve takes unfiltered flow from the brake system. The current valves being used, the spool valve, experience flow with excess debris causing reliability issues. The spool valve requires the use of a lubricant for the valve to move properly. The issues they are experiencing come down to the valve not being able to move due to the lubricant being wiped away from excess debris. We were tasked to find a new solution by selecting a new valve that limits the possible reliability issues.
All right, going off of what Abby said, before we were able to choose our valve, we were given some technical requirements from WebTech. The main requirements were that it must have 4 flow states with consistent switching, a port size of 1.25 inches in compatibility, minimize leakage under all conditions, must be able to withstand 120 psi of pressure. Lastly, it must be able to handle all environmental conditions, including temperature, debris, and vibration.
So we select this cartridge valve from Granger. The valve works in 3 steps. It's normally closed by default, opens when upstream pressure overcomes the spring force, and the opening threshold can be adjusted by using the screw on the top. As you can see here, the steel body and the block-mounted design make it durable and easy to maintain in a harsh rail environment. And with the max rating of 5,000 psi, it comfortably covers our operating pressure of 120 psi.
Moving on to the analysis section, we have performed CFD analysis and FEA analysis on the cartridge valve. So for the CFD, we tested for both pressure and temperature, and the fluid chosen for the CFD test was air. And on the right, we have the FEA test with these 2 fixture points and this force applied to the cartridge valve. And based on both the FEA and CFD tests, we can conclude that the cartridge valve.
So for next steps, since we've completed our CFD, FEA, and DFMEA analysis, future work would focus more on improving and validating the design further. If we had more time, we would move into full physical testing to compare our simulation results with the real-world performance, especially under different pressure and temperature conditions. We could also explore optimizing the internal geometry of the valve to improve flow efficiency and reduce losses. In addition, testing different material or coating could help increase durability and reduce wear over time. Overall, the next phase would be taking the design from validated concept to fully tested and optimized solution ready for implementation. Thank you.